In this paper, we present a new approach to animate avatars for current consumer-grade VR devices. Our system uses a neural network to estimate the user's body orientation only based on the tracking information from the head-mounted display and the hand controllers. Then it uses this direction together with the velocity and orientation of the head-mounted display to build a feature vector that fits a customized motion matching algorithm. Our approach can provide a large variety of lower body animations while correctly matching the user orientation, which allows representing not only forward movements but also stepping in any direction. Consumer-grade VR devices come with a head-mounted display and two controllers. However, previous methods use additional trackers or inertial measurement units either to predict the lower body animation or apply inverse kinematics, which introduces an additional cost to the system. VR applications and video games animate full body avatars with fixed animations, dragging the character or applying inverse kinematics to simulate the walking procedurally. These solutions either introduce foot sliding or look too artificial. With motion matching, we can produce natural looking animations for different velocities and directions. Our method consists of three components: body direction prediction, motion matching, and final pose adjustments. First, a neural network predicts the body direction using only the device's information. Second, the predicted body direction, the velocity of the head-mounted display, and the current pose of the avatar are used in a motion matching search to find the next pose. Finally, the arms are animated by applying inverse kinematics with the end effectors in the hand controllers. One approach for training the neural networks is to input the trackers and body direction information from the training set, and then compare whether the predicted direction is similar to the ground truth. However, this approach does not provide great results because the network can minimize the training error by just imitating the input body direction. Instead, for every element in a training batch, we recursively predict the direction 50 times and only compare the last predicted direction with the ground truth data. The resulting network is able to predict the body direction by using the tracker's information and maintain the temporal coherence by using the previously predicted direction. The input of the neural network is body size independent and therefore it can be used by different users without retraining. Once the body direction is predicted, together with the user's future positions estimated from the head-mounted display's velocity, we create the trajectory features. These contain three positions and directions in the future, and define the trajectory the avatar has to follow. The final query vector used from the motion matching search is also composed of the current pose, which is the position of the feet and their velocities, plus the velocity of the hip joint. The search will compare the distance of the query vector to all poses in the animation database. The closest pose will be selected and the following poses will be used in order until a new search is computed after some frames. Our method also supports non-upright motions by switching the animation database based on the head-mounted display height. By preserving pose features when changing the database, we can find smooth transitions. Switching the animation database can be useful in other situations. For instance, we can animate the avatar with different gaits or walking styles. All these changes are achieved by changing the database without the need for extra manual work. Our method could also be used for dancing applications. The dance will automatically follow the movements of the head-mounted display and consistently align the user and avatar orientations. Since motion matching can return trajectories that deviate too much from the user's actual position, we enforce the avatar to always be located at a maximum distance from the user. This is what we call position accuracy, and it provides a trade-off between the animation quality and the correct positioning of the avatar. For example, a position accuracy of 10 centimeters may be suitable for self-avatars, but it may produce foot sliding for some movements not represented in the animation database. contrary, a position accuracy of 30 centimeters gives more flexibility to motion matching to find a better trajectory, but may deviate too much from the user's position. Therefore, it could be helpful for representing other users' avatar for collaborative VR. The quality and coverage of the animation database have a significant impact on the final animations. We compared the same user movements for our complete database and two reduced versions with 25 and 10% of the poses. It can be seen how the small database struggles to find correct trajectories to follow the user and affects the final animation. Here we present more comparisons with current VR video games using full body avatars. It can be seen how our method produces natural looking movements even when the user is rotating in place. We can also predict the body orientation instead of using the head mounted display's forward direction. Our system can also be used with only one head mounted display since it is the only tracker needed to create the trajectory features for the search. As motion matching returns a full body pose, we can disable the inverse kinematics for the arms and still get high quality motions. More details are available in the paper. Thank you for watching.